Welcome back to PR Tech Talk. Today we're going to take a look at the PWM on the STM32 G071, but you can do the same for every STM32 as well. I will be mainly using the HAL libraries and the STM32 PWM, and I will start by using or looking into the clock tree and the clock generation, because that is very crucial for every application, but specific this PWM. So I hope you think it's interesting and tag along. We start by opening the project in STM32 Cube IDE. So we go with Nucleo, and that is the board that I'm using. We have it there. We give it a project name. Here we have the project now in the Nucleo Cube MX, and we will be starting by looking at the clock configuration, because that is a crucial part of every design and that is often neglected. So if we take a look into the system core, we have the sys, that is a serial wire that we need to have in the first place. But then when it comes to the clocks, we'll go under the RCC tab. And here we can see where we have our clocks, and I will be using the high-speed internal clock today, so I don't need any external crystal or oscillator, so I will disable these. So, and now those pins were put to yellow because they were not used in this case. Okay, so now we can go into the clock configuration tree. And if we first take a look here up in the left corner, here we have the low speed domain, we can say it like that. And the blue box says here LSI-RC. So it's a low speed internal, and it's 32 kilohertz. And you also have a grayed out box here called LSE, and that is grayed out due to that we disabled this one. So if I put enable on this one again, you will see that now I have available also the 32 kilohertz external clock, but we won't use that, so we will take that away again. So now we have only the 32 kilohertz internal clock for low speed internal, and we also have this blue box. It says HSI, it stands for high speed internal. So these two clocks are always available for you. And on this device, it's on 16 megahertz, and you can't change that. That is a fixed frequency. When it comes to the low speed, 32 kilohertz, we won't use that one in this application. That is mainly due for RTC and power down application. So we will use the high speed internally. And then we can see that the time or the clock is put out here. It's the HSI going into this selector and the multiplexer. And so that one is now blue, and that means that this one is selected. So there is the path of this one. So there is a path going here. So we have a divider by 1, and we have a multiplier by 8, and then we have another divider by 2, generating a PLL clock into that one. But you can see that is not blue. That means that that is not selected at the moment. We also have another path here from the high-speed internal clock going up to this divider that is divided by 1, and then it's into this multiplexer, and there we actually have the blue button. We can change this if we want to another's, but I will stick with the HSI in this application. So we will take the 16 megahertz divided by 1, and that gives us 60 megahertz. And then we have an AHB prescaler. It's also set to 1, and then I get the clock frequency on 16 megahertz here. I will actually drive it on to a higher clock frequency. I would like to run it on 60 megahertz. So I just run 60 and hit enter, and it says it didn't find any solution for the current source. Do you want to use other sources? And I just say yes. And then automatically you can see it changed from my HSI into the PLL clock instead. And it also changed the multiplier and the divider to give us this 60 megahertz. So it's very neat functionality that you get within this clock configuration. So you get this 60 megahertz. And in this application we're going to do today, we're going to look into the PWM generation. And that is actually the reason I choose 60 megahertz instead of the maximum 64 megahertz. And that will be coming more clear in a bit. But you can for sure use whatever clock frequency you want here. And when it comes to PWM, that is driven by the clocks, the timers. And the timers are then sourced by this clock here. And the timers that we are using is driven from this APB timer clock. So we can see that we have 60 megahertz coming to the PWM timer that we will be using. So that is the input clock for this application. So it's not anything dangerous to do anything here. You can always just put your values here if you want to have 32 megahertz, and then everything changes. You can see here, then you get the 64 megahertz to that one, and if you don't like that one, you can change that to 32 megahertz, and then everything else changes. But I would like to have it like 60 megahertz, so I will change that one. And now I have 60 megahertz on all outgoing clocks. You can actually also measure the clock that you have internally if you would like to. So you have this here, the MCU clock source multiplexer. So where you can actually have an output. So this is an output. You can see the small arrows down here. That is output from the clock configuration. And to enable this one, we need to go back to the pin configuration. And here we can see that we have the master clock output. So if we put that one and we go back to the clock generation, now we can see that this box here is blue. And you can also have here the what do you want to put out on this output pin. So the MCO pin. So I would like to have actually the system clock, and that is the system clock we have here, sys clock. So I can select that one, and then I will get 60 megahertz out of it. And if that is too high frequency for me, I can divide it down, and I can see that I then get a different frequency. And I can also select other crystals. For instance, if I would like to have the low speed internal, this crystal or this oscillator, 32 kilohertz. If I would like to have that to drive something other outside of the device, I can select that one, and I get 32 kilohertz out on that pin. I can also use the high speed external, but I didn't select that one, so it won't be enabled. And I can use the high speed internal clock. So I take this clock and I output it, then I get 60 megahertz and not the 60 megahertz that I have on system clock. And the reason for 60 megahertz is this PLL that it goes through, that it multiplies up the frequency for you. And you can also have the PLL clock, and so you can choose whatever you want to have there. But I don't want it in this application, so I deselect that one. So just to make a resumption, now I have 16 megahertz going through the PLL source multiplexer, and it goes into the PLL clock, into this multiplexer, giving out the 60 megahertz, and I will use that 60 megahertz to drive everything in the device. And the 60 megahertz is what we need for the PWM block. When we're talking about PWM, we actually talk about many things, but mainly there are three parts. That is the frequency, duty cycle, and resolution. And the frequency is how often a period, full period, that it means both the T on and the T off. So both the T on and T off together is a period. How often this occur in 1 second. And what we are doing in this elaboration, we will have 100 kilohertz frequency. And the duty cycle, that is how the portion is between the T on and the T off. So if the duty cycle is 30%, for instance, then the T on is on for 3 microseconds and off for 7 microseconds. And then the resolution, that is how many steps or how accurate can you actually put the 30%. How many steps can you take? And in this application we are going to use 100 steps. So that means for one period we have 100 steps in total. So these need to be divided on both the T on and the T off. So for the 30% application, then we have 30 steps for the T on and 70 steps for the T off. We will be using the timer 2 in this demonstration. And it gets its clock from the EPB clock source, and we set that on 60 MHz in this application. So we source the timer 2 with 60 MHz, and then there is a register, a prescaler register, that we set to divide by 6. So after this prescaler we then get 10 MHz that we put into the TIM2 counter. So the TIM2 counter is counting from 0 and up with the frequency of 10 MHz. And then we also then set the TIM2 ARR auto reload register to 100. This actually sets 2 parameters. It both defines the resolution, but also in conjunction with the 10 MHz input, we also define what clock frequency or the PWM frequency. So setting this ARR1 divides the 10 MHz input clock with 100, and that gives us 100 kilohertz. And it also gives us 100 steps in resolution. So the counter will count from 0 and up to 100 and then reset down to 0 again and just continue like that. Then there is another register also called capture compare register in the TIM2, and that we set initially to 30. And what it does then, it sets and the counter starts from 0 and 1, 2, 3, 4, and when it comes to 30 we have the capture compare register, and then you see the TIM2 channel 1, it pulls from the high level to the down level, and having the level low for the remaining of the pulse until we get to 100 in the counter, where we reset and we start a new sequence again. So by changing the CCR register, we can change the pulse quote from 0 to 100%. So if we open the timers, we see that there are a lot of timers, and I would actually like to have the timer out from the microcontroller. And there we have an LED put on the board, LED green. And if we highlight that one, and we can see that there is actually timer 2 channel 1. So if I just put that one, it means that that one is yellow. It's not completely configured. It needs to be done something more with it. So we go with timer 2, and I said also timer 2 channel 1, because every timer have various number of channels, and timer 2 have 4 channels, as we can see here. And the channel 1, that is disabled at the moment, but we would like to have PWM generation channel 1. So now if we click that one, we see automatically that this pin is then green. But the timer 1 also need to have some clock, and we go with the internal clock. And we knew from the previous, if we go up on the clock configuration, it's driven from this 60 MHz. So we will put in 60 MHz in the internal clock, and we have the PWM generation channel 1. Then we can look on to the configuration. Just open up a bit. We then have a prescaler, and the prescaler stands for the 60 MHz. Do you want to have all the full 60 MHz when you're doing your PWM, or do you want to make something lower from that? And in my case, I had 60 megahertz, and I would like to have a number round up to 1. So I will do like this. I will divide that by 6, because then it gives me 10 megahertz input clock. 60 divided by 6 is 10 megahertz. So we put 6 there. But now there's a tweak. From the very beginning, it said 0. So 0 is actually 1. It's a bit odd, but so if you would like to divide it by 6, you need to put 6 minus 1. That is the easiest way to do it. Or you can just put 5 there as well. But trust me, if you put 6 minus 1, you divide it by 6, so you will get 10 megahertz. And then you will have the counter mode and what we would like to count, and we can just leave it with counting up. So it will count from 0 up to 10 million. And then we have a period here. And we said that there were 3 parts, and that was frequency, duty cycle, and resolution. And here is where you actually put the resolution. So if I put 100 here, that means that I have 100 steps for the full cycle. So if I put the full sweep is 100 cycles, I can then select how big portion of the 100 that should be high and how it should be low. So if I have a 50% duty cycle, that is symmetrical, then I have 50 high and 50 low. That makes 100. Or 30-70, that is 30 high, 70 low. So we put 100 here. Also, there is another thing with it. Now that I have 10 megahertz coming from the prescaler after the prescaler, since we scaled it down by 6, I have 10 megahertz coming into the counter. And the counter then counts up to 100. That means that we get an output frequency on 100 kilohertz. So we will get a signal on 100 kilohertz out of this one. So the frequency is 100 kilohertz, and the resolution is also 100 steps. So that is the reason for me driving 60 megahertz instead of 64 megahertz, because then it wouldn't be even. Then we can go down all the way down to here, and the pulse. And the pulse is the duty cycle. So if I would like to have a 30% high, then I just write 30 here. And, sorry, I forgot one thing. I need to also add -1 here. Yeah, it's the same as the prescaler. The counter period, you also need to have -1. However, on the pulse, you don't need that. It's fully logical. So pulse 30, so that is the value. That is all you need to do for the PWM timer. So we can now save all and generate the code for us, and also change the perspective. Great, so now the project is done for us. If we go under here and we can take a look on the source, we have the main file here, and we can see what it had done. It had MX time 2 in it, and there is also the USART. We won't be using the USART, so we could actually put that away. And it initialized also the timer 2, and if we take a bit lower down here we have the timer 2. So here we can see what we did on the prescaler. We said 6 minus 1. We have that here. And also the period we have here, it's 100 minus 1. So we get 100 kilohertz, or we will look into that and actually put it on a scope to see that we actually get what we hope that or think that we get. And also the period, or the duty cycle we have down here, is the pulse. So it's 30. So we will have a 30% pulse quota. Great, we can just build it to see if there is any errors, but I haven't entered any code manually yet, so I would be very surprised. And as usually, it's done correctly. However, if we now start and just compile the code, we won't get any PWM output. We need actually to start the PWM peripheral to get the output. We need to do it after the initialization. So we go with user code begin 2, and there is a place where we can actually put in code, and where we actually had mx time 2 initialized already, so that is a good place that we could use. And we get start. And we have the h time 2, that is the handler for it. And we also need to have the channel. Tim channel 1. You can't just write 1 here, because if you look in and hover over it, you see what the macro actually refers it to. So that is 0. So if we should do something and not using the macro, we should then use just the number 0. But it's more clear to have the Tim channel number 1. So now we have the HAL Tim PWM start, and the handler is the Tim2, and that is already defined for us by the CubeMX and the channel 1. So now when we compile this one, it will then enable the PWM for us. We try to debug it, and we go with the debugger, and we hit the ST-Link serial, and we scan to see if we have connections with the, and we see that there is a serial number. That means that we at least have connection to 1. We can also have this going down. If we have several boards connected to our application, we can actually see several of these. So we can have more than one. That is a question I got before. Can you actually have more than one debugging? If you, for instance, have one that you would like to send data from one microcontroller to another microcontroller, can you have 2 simultaneously debugging? And yes, you can. You need then to change which debugger you would like to talk to in which session. In this case, I only have one, so I select that one. So now we are in the debugger, and we can start the program by hitting this icon, and we don't see much what is happening. But if I run in my trusty oscilloscope from Analog Devices called Scopy, we can see that we actually have now the waveform. And I have put 2 cursors here. And if we just remove those 2 cursors like so, and we put them there. So between the cursor 1 is the gray one there, and the other cursor is the cursor 2. So we can look up here in the statistics. We see that the period is close to 10 microseconds. And that gives us 100 kilohertz as we aimed for in our code. So 60 megahertz divided by 6, that gave us 10 megahertz. And then we had 100 count steps, that gives us 100 kilohertz. So 100 kilohertz, and that is a period of 10 seconds, or 10 microseconds. So we have 10 microseconds from this event to this event. So this is one full sweep. And you remember the 100 that we said a count period. If we start by thinking that we count with 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, until we come to 30, because we set it, the pulse width to 30. Then the pulse width says, okay, now we change to the low period, and then it continues to count all the way up to 100. And then that period is done, and then the next period comes on, and then it goes up again. So here in between, we expect now to have 3 microseconds between this upgoing flank to the downgoing flank, and we can measure that by moving this cursor to this flank approximately. It's very hard to get it exactly, but close to it. And we can see that there is a delta on 3 microseconds. between the first cursor and the second cursor. So that means that that is correct. That is 30% high and 70% low. And we then go back here and we can then measure how long the low period is, and that should be 7 microseconds. Yes, 6.9 microseconds. So that is also the 70% that is low. And the full swing from beginning to the end, that is 10 microseconds, the same that we see up here, and that gives us 100 kilohertz. So this pulse is now 100 kilohertz with a resolution on 100 steps, and the pulse quote or the duty cycle, that is the same, is 30%. And we can then change the pulse quote as well. If we remove this one and we stop the debug. Okay, so now I tried to rearrange the window so we can have both the scope meter and the code in the same view at the same time. To change the pulse quote, we see here that now we have the 70% pulse quote as we defined earlier. But if we want to change that, we can actually do on a different version. We can actually alter the capture compare register directly. So we have the timer 2 that we are using for this PWM, and we have then the channel 1, and the channel 1 then have a capture compare register. And if we enable that, or if we change that capture compare register directly, we can now, let's say it's like 30, and if we change it to 50, then we would get a 50% duty cycle. So we try with this one and just build a project, and there were no warnings, no errors, and we download the code to the. So we should see now that the code will have a high pulse for half the sequence. So there, now we have 50-50. So now we have a full, still 10 microseconds duration, and the frequency is still 100 kilohertz. And if we change this marker, we see now that the delta is 5 microseconds. So it's 50-50. So that is one way to do it, changing the capture compare register directly. But there is also a HAL version of doing it. So if we just comment that line out and we go with the HAL. So this is a special one. You need to have double underscore here in the beginning. So it's not one underscore, it's a double underscore. So HAL time set compare. So this is the capture compare register. What timer should we apply this one? It's to the timer 2 and to the channel 1. And then what should we set it to? And then I just put an I there. So I is a variable that we need to also define. So if we go up to, now let's see, where do we have it there? The user code begin PW. So there I have just declared the I as an unsigned integer, an 8-bit. So, and further, where was it? Like so. And now the I is not, it's just declared, it's not initialized. So we need to give it a value. So if we say I equals 85, for instance, just so that we get something that is different, and we try to compile it, and we download it. So now the high should be about here something. since it's 85%, or actually down here, yeah. So we see, then we have 85, we can see on the cursor there it's 8.5 microseconds, and then we have the full scope on 10 microseconds. So that is another way that we can do. And now that we have a variable that we set here, we can actually start doing some work on this one. So if I just delete these and I go down in the main loop instead, and I have prepared some small code for us. Like so. So this is a while one loop, so it will loop here forever, always. So what we do, we take the I and we declare it to 0, and as long as I is less than 100, we increment the I by 1, and then we use the same feature __ her time set compare to the capture compare register, and after that we have set the time. We have a small delay, and then it loops all the way to it when it's until it's 100. Then it goes out of this loop and it goes down to this loop, and we do the same thing but opposite. So we decrease it from 100 to 0, and when this is done, then we go back and start over again. So now we will see a sweeping duty cycle from 0 to 100 and from 100 to 0. So that is exactly what we see now. So this is the full scope of, so here is 100 steps for each, and we have, I think I said 10 milliseconds. Yeah, 10 milliseconds. So we have 200 milliseconds for the full sweep here, or 2000 milliseconds. So it's a 2 second from start to beginning to end. So now we have 100 kilohertz frequency. So the frequency is 100 kilohertz. The duty cycle is varying, as we see. And if this would now be an LED, the LED would be going up and down in intensity. And also, if we had, for instance, a motor, the motor would be speeding up and down. It would not be nice that it would be changing so fast. But that is actually what PWM does for you. Hope you learned something new about PWM. If you did, please give it a thumbs up. And if you're not a subscriber yet, please hit this round icon beneath me down here, and then you will be automatically a new subscriber. Also take the opportunity to take a look on my other videos. I think it's that way. For my other, I have my playlist there. I think I have like 30-40 videos on STM32. And if you have some comments or on this video or suggestions on new video stuff, please give me some comments in the commentation field. It's highly appreciated. So until I see you next time, stay safe. Bye.